All right, ready for this? Today, we're doing a deep dive on differential equations.
Ooh, cool.
Yeah, I know, I know. It sounds a bit intimidating, maybe,
Yeah, maybe a little.
but trust me,
Yeah,
this stuff is seriously cool once you kind of get into it.
it really is. It's like they're everywhere. Like you don't even realize.
Bro.
Differential equations are like, how do I describe it? They're like the secret code
Yeah,
to how everything changes.
yeah.
Like in the universe.
Everything.
The motion of planets to like how trends spread on social media.
To how this podcast is even, going out.
Oh, yeah.
Okay, so back up for a sec. What is a differential equation? Like literally, like what are we talking about?
Imagine you're like piecing together a puzzle,
Okay.
but you don't have the whole picture, right?
Right.
You only have like snapshots of how the pieces are moving.
Okay.
So those snapshots are like derivatives.
Okay.
They tell us how a function is changing. And our job is to kind of figure out what that original function is.
Oh, okay. So it's almost like a detective story.
Yeah.
Where you have clues about the culprit's movements,
Yeah.
but you have to build, a picture of who they are
Exactly.
and where they've been.
Yes. And the thing is, one differential equation, right?
Okay.
It can have like a ton of possible solutions,
Yeah.
right? Because you could have lots of different culprits.
Right. Different ways to get there.
Exactly.
Okay, so how do we narrow that down then to like the right solution? We need more information, right? We need something else.
Yeah, you're totally right.
Yeah.
That's where initial and boundary conditions come in.
Okay.
They're like giving the detective
Yeah.
a starting point
Okay.
and some boundaries for their investigation.
Okay. I like that. I like that a lot. So let's break it down, right? What exactly are initial conditions?
Think starting state.
Okay.
Um, Like if we're studying how a population grows
Okay.
over time, right?
Yeah.
Initial condition might be, what's the population size
Right.
at year zero?
Yeah. Got it.
Yeah.
Okay, so that sets the stage. What about boundary conditions?
They're like, they define how a function behaves
Okay.
at the edges of its world.
Okay.
It's like setting limits on where our culprit can go.
Okay.
So imagine you're trying to understand
Yeah.
how heat spreads through a metal rod,
Yeah.
right? Like a blacksmith is working on.
Oh, okay, yeah.
Boundary conditions might be, what's the temperature
Right.
at each end of the rod?
Oh, I see. Okay. So without those boundary conditions, it could be like glowing white hot in the middle,
Exactly.
but ice cold on the ends, which doesn't make sense.
Yeah, it wouldn't make any physical sense.
Right.
So it's like making sure our culprit couldn't have teleported across town.
Right. Exactly. Okay. This is making more sense.
Mhm.
This is making more sense. But honestly, like, why are these conditions so important? Besides just getting like the right answer, what are they really telling us?
You've hit on a key point there.
Yeah.
It's not about just finding a solution. It's about finding the one
Right.
that matches reality.
Okay. Yeah.
Like, what if the detective had multiple suspects,
Right.
but they all fit the clues?
Yeah.
Without more information, he couldn't say who did it.
Right. So initial and boundary conditions are like they're helping us sift through all the possibilities to zero in on like the truth.
And they do even more than that.
Yeah.
These conditions are often based
Yeah.
on real-world data.
Oh.
So they're the link
Yeah.
between like the abstract math
Right.
and the tangible world.
So it's grounding the equation
Yeah.
in reality. It's not just like some theoretical,
Yeah.
you know.
It's tied to something concrete.
Right. Yeah, exactly. It's gotta be applicable to something somewhere. Okay, so this connection to real data, this is what lets us like use differential equations to make like predictions.
Yeah, exactly.
And test our understanding of the universe.
Mhm.
Right? It's how we go from like equations on a chalkboard to launching rockets.
Yeah.
Or predicting the weather.
Exactly.
Oh.
And there's another fascinating
Okay.
aspect of these conditions.
Okay.
They can reveal
Yeah.
how sensitive
Yeah.
a solution is
Okay.
to small changes.
Okay.
We call this stability.
So is that like the butterfly effect,
Yes.
where a tiny change can lead to massive differences?
Yeah. Imagine two scenarios.
Yeah.
They're almost identical.
Yeah.
but just a tiny difference
Yeah.
in one of the initial conditions
Yeah.
could lead to a huge change in the outcome.
Oh, wow. Okay.
So like choosing one path over another at a fork in the road,
Right.
you know, a small decision could lead to completely different destinations.
Yeah. Okay. Okay. So these seemingly minor details
Yeah.
can have massive consequences
Yeah.
for how a system like evolves over time.
Exactly.
This is wild. Okay, so we talked about like why these conditions are important,
Mm-hmm.
but are there different types?
Yeah, you bet.
Okay.
And understanding the different types is key to using them correctly
Right.
in different scenarios. Let's start with Dirichlet boundary conditions.
Okay, that sounds fancy. What's that all about?
It's simpler than it sounds.
Okay.
Dirichlet conditions specify
Yeah.
the value of the function
Okay.
at the boundary.
Got it.
So think back to our blacksmith
Okay.
on the metal rod, right?
Yeah.
If we fix the temperature at one end
Okay.
to a specific value,
Yeah.
say 100 degrees,
Okay.
that's a Dirichlet boundary condition.
Got it. So it's like you're setting a fixed
Yeah,
temperature.
exactly. Now, on the other hand, we have Neumann boundary conditions,
Okay.
and those specify the derivative
Okay.
of the function at the boundary.
Okay, hold on. So instead of setting like a fixed value, we're setting how more the function is changing
You got it.
at the boundary.
What often relates to how much of something
Yeah.
is flowing
Yeah.
across that boundary.
Okay.
So, for example, if we're modeling the spread of heat,
Okay.
a Neumann condition
Okay.
might specify how much heat is being transferred
Right.
at the edge of our system.
Okay. Okay. So Dirichlet's like setting the level of something,
Mm-hmm.
and Neumann's like setting like the rate at which something is flowing
That's a great way to think about it.
in or out. Yeah.
Now, there's one more type we should cover. Robin boundary conditions,
Okay.
or sometimes called mixed conditions.
Mixed conditions. Okay. This is where it gets complicated.
Well, they are a bit more complex,
Okay.
but they're also more realistic
Okay.
for some situations.
Right.
So Robin conditions combine elements
Yeah.
of both Dirichlet
Okay.
and Neumann.
Oh, wow. Okay.
So they specify a combination
Okay.
of the function's value and its derivative at the boundary.
So it's like setting the level and the flow rate.
Exactly. So these are particularly handy when the boundary is interacting
Yeah.
with its surroundings
Right.
in a more intricate way.
Okay, this is all starting to feel very tangible, but I think like a real world example would really help.
Yeah.
Cement it all.
Sure.
Like what kind of scenario would bring these concepts to life?
I got one.
Okay.
Imagine we're modeling the spread of a disease
Oh, okay.
through a population.
Oh, wow. That's timely. Yeah.
Okay. So what would the initial and boundary conditions be in that case?
So the initial condition could be like the number of infected people
Okay. Yeah.
at the very start of the outbreak.
Right. Like patient zero.
Yeah, like patient zero.
Like that crucial
Yeah.
starting point.
Yes.
And what about the boundaries? What would those be in a situation like that? Like, it's not like it's a physical object with edges, you know?
You're right.
Yeah.
The boundaries here aren't physical, but they're still important.
Okay.
So they could represent factors
Yeah.
that limit
Yeah.
the spread of the disease.
Okay. Yeah.
Right.
Yeah. Yeah.
So things like the rate at which people
Yeah.
enter or leave an area,
Right.
or even behavioral things like mask mandates,
Yeah.
social distancing guidelines.
So those would act like barriers.
Exactly.
Right. That influence how quickly
Mm-hmm.
the disease spreads.
And by tweaking?
Those boundary conditions.
Yes.
In our model,
Yeah.
we can explore
Yeah.
how different interventions
Right.
might impact the course of the outbreak.
So you're running simulations
Yeah,
to
basically.
see how different public health policies
Yeah.
could affect
Mhm.
the spread.
Exactly.
Oh, that's incredible.
Yeah.
But I'm curious, how do you actually translate those real world scenarios,
Yeah.
into like the mathematical, the conditions?
Mhm.
It seems like a pretty big leap.
It is a complex process.
Yeah.
But that's where the magic of differential equations comes in.
Okay.
We use mathematical terms
Yeah.
to represent things like transmission rates, recovery rates,
Okay.
even things like the effectiveness of vaccines.
So you're creating a mathematical language
Yes.
to describe the dynamics of the disease.
And by combining that language with the right initial.
Yes. And boundary conditions. Yeah. We can build a model that captures the essence of how the disease is spreading.
So those conditions aren't just like abstract math concepts. They're the key to bridging like theory and reality.
They give us a really powerful tool for understanding and predicting how the disease might evolve.
Okay. So this is all really fascinating. But I have to admit, when I hear differential equations, I still get a little intimidated.
Sure.
Any advice for people like me who are just starting to like wrap their heads around these concepts?
Don't worry, you're not alone.
Okay.
It's a challenging subject.
Yeah.
But it's definitely within reach.
Okay, good.
My top tip is to start with visual examples.
Okay.
It's much easier to grasp these concepts when you can see them in action. So instead of just looking at like equations on a page, try to picture what they represent in the real world.
For instance, imagine a simple pendulum swinging back and forth.
Oh, okay. I can see that.
Right. The angle of the pendulum and its velocity at any given time is governed by a differential equation.
Okay, so we could use that equation then to predict where the pendulum's going to be.
Exactly.
And how fast it'll be moving at any point in time.
Yes. And we could even experiment with different initial conditions. Like releasing it from different heights.
Right.
You see how that affects its motion.
Yeah, so it's a hands-on way to understand how those initial conditions shape the solution.
Exactly. And as you get more comfortable with those basic examples, you can gradually explore more complex scenarios.
Right. Yeah.
Like the heat flow problem we talked about earlier.
Speaking of the heat flow problem, can you walk me through how we'd actually define those boundary conditions?
Of course.
Because I'm still a little fuzzy on that part.
Let's imagine you're baking a loaf of bread.
Okay.
In a rectangular pan.
Right.
And the sides of the pan are insulated.
Okay.
Meaning no heat can escape.
Got it. So the sides are like perfect barriers.
Exactly.
To heat flow.
Which means the temperature gradient at the sides of the pan is zero.
Okay.
There's no change. In temperature.
Okay.
As you move from the inside of the bread to the edge of the pan.
So that would be a Neumann boundary condition.
Right. You nailed it.
Specifying the rate of change, or in this case, no change.
Exactly. Now imagine the top of the loaf is exposed to the oven's heat.
Right.
Here we might have a Dirichlet boundary condition where we specify a fixed temperature.
Right.
At the top surface of the bread.
Ah, I see. So different parts of the loaf can have different types of boundary conditions.
And by incorporating those conditions into the heat equation, we can build a model that predicts how the temperature inside is going to change as it bakes.
That's so cool. It's like we're using math.
To
create a virtual oven.
Exactly. And by adjusting those boundary conditions. Like changing the oven temperature or using a different pan. We can explore how those factors influence the final outcome.
This is all starting to click. This is amazing to see how these seemingly abstract mathematical concepts have such tangible applications in the real world.
And that's just the tip of the iceberg.
Oh, really?
Differential equations are used.
Oh, wow.
In countless fields. From engineering and physics to finance and medicine.
So it's really a foundational language for understanding and describing how things change.
And as we continue to push the boundaries of science and technology, these equations are just going to become more and more important.
Okay. This has been incredibly enlightening. I'm starting to see differential equations in a whole new light, but I have to admit, my brain is starting to feel a little full.
I understand.
It's
a lot to take in. So let's pause here.
Okay.
And return for the final part.
Right.
Of our deep dive.
Okay.
Where we explore some of the broader implications of these powerful mathematical tools.
Looking forward to it. Welcome back to our deep dive on differential equations. I'm still trying to wrap my head around all the amazing applications.
Yeah. We talked about from predicting disease outbreaks to simulating a baking loaf of bread. It's incredible how these equations connect math to the real world.
It really does. It really highlights the power of mathematics as this language to describe.
Right.
And even, predict how the world works.
Yeah.
And the cool thing is we're just scratching the surface.
Wait, there's more.
Yeah.
I thought we'd covered pretty much everything at this.
Oh, there's always more
to
discover.
Right.
For example, remember how we talked about stability and the butterfly effect? Well, that concept is hugely important.
Okay.
In chaos theory.
Chaos theory.
Yeah.
Like the idea that even tiny changes can have unpredictable, massive consequences.
Exactly. It's the study.
Right. Of systems that are highly sensitive to initial conditions.
Okay.
Think about weather patterns.
Yeah.
Even with incredibly powerful computers and tons of data, it's still hard to predict the weather accurately.
Right.
Very far in the future.
Right, because even the smallest error in measuring the current conditions could lead to wildly different forecasts.
And that's where differential equations come in.
Okay.
They're the tools that we use to model those chaotic systems.
Okay.
To try and understand how they behave.
Yeah.
And maybe even predict how they evolve over time.
So it's like trying to map out all the possible paths that those tiny changes could take and how they could ripple through the system.
Yeah, it's a great way to think about it.
Yeah.
It's a fascinating and challenging field.
Yeah.
And it has implications for everything from climate science to economics to even understanding the human brain.
Wow. So differential equations they're like the key to unlocking some of the biggest mysteries.
They really are.
In the universe.
And what's even more exciting is we're constantly developing new mathematical tools and techniques to tackle even more complex problems.
So it's not just about solving the equations we have.
No.
It's about inventing new ones.
New ones to describe.
Yeah.
Phenomenon we're only just beginning to understand.
That's pretty inspiring. Makes me wonder if someone wanted to dive deeper into this world, where would they even begin?
I would say the best place to start is by exploring your own interests.
Okay.
What are you curious about? What problems do you want to solve?
Yeah.
Once you have a topic that excites you, then you can start looking for resources.
Okay.
That connect differential equations to that field.
That's great advice. It's a reminder that math isn't just some abstract concept.
Yeah.
It's a tool.
It's a tool
for understanding and engaging with the world around us.
I couldn't agree more.
Yeah.
And honestly, the more you explore, the more you'll realize just how interconnected everything is.
It's like differential equations are the threads.
Yeah.
That weave together all these different fields.
That's a beautiful way to put it.
Yeah.
They show us that even seemingly unrelated phenomenon often share underlying mathematical principles.
This has been an incredible journey. I feel like I've gained a whole new appreciation for the power and beauty of math, especially differential equations.
I'm so glad to hear that.
Yeah.
It's been a pleasure sharing this deep dive.
Absolutely. So to everyone listening, if there's one thing to take away from this deep dive, it's that differential equations aren't just some arcane mathematical concept. They're a fundamental language.
Yes.
For describing change.
Yeah.
And they're at work.
Yes.
All around us, shaping the world in countless ways.
That's right.
So keep exploring, keep asking questions. You never know what incredible insights you might uncover.
Welcome back to our deep dive into differential equations. I'm still trying to wrap my head around, all the amazing applications we talked about, from predicting disease outbreaks
to simulating a baking loaf of bread.
Yeah.
It's incredible how these equations connect math to the real world.
It really highlights the power of mathematics as a language to describe and even predict how the world works.
Yeah.
And the cool thing is we're just scratching the surface.
Wait, there's more?
Oh yeah.
I thought we covered pretty much everything at this point.
Oh, there's always more to discover.
Oh, okay.
For example, remember how we talked about stability and the butterfly effect? Well, that concept is hugely important in chaos theory.
Chaos theory. Okay. Like the idea that even tiny changes can have unpredictable, massive consequences.
Exactly. It's the study of systems that are highly sensitive to initial conditions.
Right.
Think about weather patterns.
Yeah.
Even with incredibly powerful computers and tons of data.
Right.
It's still hard to predict.
Yeah.
The weather accurately very far in the future.
Right, because even the smallest error in measuring the current conditions could lead to wildly different.
Exactly. And that's where differential equations come in.
Okay.
They're the tools that we use to model those chaotic systems, to try and understand how they behave,
right,
and maybe even predict how they evolve over time.
So it's like trying to map out all the possible paths those tiny changes could take, and how they ripple through the system.
It's a great way to think about it. It's a fascinating and challenging field. And it has implications for everything from climate science to economics to even understanding the human brain.
So differential equations are the key to unlocking some of the biggest mysteries.
They really are.
In the universe.
And what's even more exciting is that we're constantly developing new mathematical tools and techniques to tackle even more complex problems.
So it's not just about solving the equations we have. It's about inventing
new ones.
New ones.
To describe phenomenon we're only just beginning to understand.
Oh, that's pretty inspiring. It makes me wonder if someone wanted to, dive deeper into this world, where would they even begin?
I would say the best place to start is by exploring your own interests.
Okay.
What are you curious about?
Right.
What problems do you want to solve?
Right.
Once you have a topic that excites you, then you can start looking for resources that connect differential equations to that field.
That's great advice. It's a reminder that math isn't just some abstract concept.
Yeah, it's a tool.
Yeah, it's a tool for understanding and engaging with the world around us.
I couldn't agree more. And honestly, the more you explore,
yeah,
the more you'll realize just how interconnected everything is.
It's like differential equations are the threads that weave together all these different fields of knowledge.
That's a beautiful way to put it.
Yeah.
They show us that even seemingly unrelated phenomena often share underlying mathematical principles.
This has been an incredible journey. I feel like I've gained a whole new appreciation for the power and beauty of math, especially differential equations. It's been awesome.
Well, it's been a pleasure sharing this deep dive with you.
Absolutely. So to everyone listening, if there's one thing to take away from this deep dive, it's that differential equations aren't just some arcane mathematical concept. They're a fundamental language for describing change, and they're at work all around us, shaping the world in countless ways.
Yeah.
So keep exploring, keep asking questions. You never know what incredible insights you might uncover